Hello, check, check. Check, check. 1, 2, 3, check. Hello. Mechanical properties of solids. Check, check. Start the ground, will you? Oh, right. Good morning, dear all students. Welcome to the nandionline video classes physics session. I hope you are doing well. Stay home, stay safe. During this pandemic situation, there is no other option for us. So let us start with physics session. In physics session, I am going to explain the topic, the chapter, mechanical properties of solids. So already briefly we revised the mechanical properties of solids in our during PUC, but this is a neat session. So I would like to explain briefly, revise the basic concepts of mechanical properties of solids, in which introduction. First of all, the elastic property, which is the deals with the property of the material. It is the property of the material, such as how its strength and what about the ability. When you apply an external force on it, how much it is going to be tolerated, or how much the strength of the material or the ability to withstand when you apply the external force. This all discussed in the case of mechanical. We are going to study about the properties of the solid when the external force is applied. When the external force is applied, what about the intermolecular forces? What about the elongation? How many types of stress are there? How many types of strain are there? How many types of modulus of elasticity? All briefly I am going to explain, because in the next class I am going to solve the objective type numericals in the module exercise 1A. So once again, elasticity is the topic or the property which deals the property of the material, such as about its strength. So in this, first of all, intermolecular forces. Obviously, you know this word, intermolecular forces. That means the force between any two molecules, the force between any molecules, because of due to interaction between the two. Suppose if you consider any two molecules, there may be a force of interaction because of due to certain distance. So there may be a force of interaction due to because of charges of the molecules. As we discussed, every molecule has its own charge. So because of due to its charge, charges, the molecule, exert intermolecular forces on each other. This causes this helps us to discuss about the potential energy between the two molecules, and as well as how the variation takes place when the distance increases between the two molecules, how the intermolecular force change. So first of all, you should know what do you mean by intermolecular force. The intermolecular force means the force between the two molecules due to the elastic, that means due to the elastic interaction. There may be interaction between these two molecules that we are calling as a elastic interaction. Because of this elastic interaction is because of the charge of the molecules. That means which are responsible for the intermolecular forces. And these forces are active, the separation between 10 to the power of minus 9 meter approximately. These forces are applicable, or these forces are active only when the separation between the two molecules are in the order of 10 to the power of minus 9 approximately. This can be taken. So in this chapter, first of all, the definitions, basic definitions. What is a rigid body? Okay, children. What is a rigid body? And what do you mean by deformation forces? Deformation forces. And what do you mean by restoring forces? These are very important here. Restoring forces. Already we discussed in the PUC. So rigid body is nothing but a body in which whose size and shape does not changes with respect, when the external force is applied. When the external force is applied on that, if the size and shape of the body does not changes, then the body is said to be rigid body. Yes or no, children? So when suppose consider a spring or a rod, when it is applied to a certain extension, definitely here what is happening, external forces are applied. So for our convenience we are taking that even if you apply large external force that cannot be changes, that means the size and the shape, there is no actually perfectly rigid body in the complete there is no rigid body in the nature. So the nearest approach, we assume that perfectly rigid bodies are not available in the nature. We will take approximately a diamond, which is a perfectly rigid body. So rigid body means a body whose size and shape does not changes. Even when you apply the large external forces, there will be no perfectly rigid body, but nearer to it we will consider as a diamond. The next one is, if you observe this example, when a spring is attached to a fixed end and the load is attached or a mass attached to it, if you just apply some external forces, then definitely elongation takes place. Yes or no, children? So here elongation will be takes place. So here the external forces which are responsible, yes or no, which are responsible. When you apply the external force, immediately there will be change in the length and size, but actually truly what is happening, when you remove these external forces, the forces which is developed inside the body or within the body, within the volume of the body, so as to regain its original position. So these external forces will always tends to, change the size and shape or length, whatever it is, length and that is called deforming forces. When the deforming forces are removed, immediately restoring forces will be developed in order to regain its original position. So here two forces should be very important. One is the external force. That external force will cause a change in the size and length of the load. That means the internal forces, actually the external force which changes the size, you should be very important, you should know that the external forces which are responsible to change the size and length, change the size or shape of the body without moving the body. That means without moving it as a whole. That is called deformation force. So it is very, very important. This is called a deformation force. So deformation forces are the forces which are due to because of external force and which will change the size and shape of the body. So once if the external forces are removed, immediately its nature, restoring forces are developed within the body, inside the body, within the value of the body, so as to regain its original position. That means these restoring forces are nothing but the forces which are developed. So this is very, very important that how these restoring forces are developed. Observe carefully. I am giving an explanation for you, the difference between deformation and because and restoring forces. This is very, very important. Suppose if a force is applied on a body normally, as a result it displaces to a delta x, assume that like that. If you are applying the force normally, then internal forces will be developed within the body like this, normal to particular area. So these are called internal forces. These internal forces are because of restoring forces. Yes. So deformation is because of due to external forces. That means these deformation forces are because of due to external forces and the restoring forces are because of due to internal forces. And these restoring forces are always opposite, equal, but they are exactly directly proportional to the deformation, but they are opposite. So we can say to two definitions are very, very important. Restoring forces. The restoring forces are nothing but these are internal forces. These are the restoring force. This is nothing but external. So restoring forces are nothing but internal forces. It is very, very important. So internal forces which are nothing but which restores the size and shape of the body when the deformation force is removed. When we remove the deformation forces, which is responsible for the change in the length and shape of the body, when we remove immediately the internal forces developed in the body is a quite nature, then the magnitude of the restoring forces we can say, only we are discussing about the magnitude. So the magnitude of the restoring forces is equal to, that means the deforming forces. So it is equal to the deforming forces. I am taking this as deforming forces just like, no, this is because of external, this is because of internal. Now, the next topic is, when the, how can you identify, how can you explain the behavior, that means the elastic behavior of a solid? Very simple. When you consider a solid, if external forces are applied, which tends to deform the size and shape of the body, when you remove the deformation forces, immediately, internally, in the body, within the body, inside the body, within values of the body, internal forces will be developed. That forces will restore its original position and they cause to restore its original position. This property of a solid, particular property, that means as we are saying, if you imagine a solid body, the solid body definitely atoms or molecules are bounded together interatomic forces, as I discussed about this, interatomic forces. Certain interatomic forces will be exist between two molecules when they are in stable equilibrium. Assume that at the stable equilibrium, that means no forces are acting on the body or the solid body, the molecules are exactly, that means intermolecular forces, that means intermolecular, or we can say the intermolecular forces together, we can also call it as interatomic forces or intermolecular forces. Yes, there are two kinds of forces we are going to study in chemistry also. There are two kinds of again interatomic forces and intermolecular forces. So at the stable equilibrium, we can say if there is no external force, there will be the intermolecular forces together, or that means there will be no change. The molecule, they are bounded with the strong intermolecular forces. Suddenly what will happen when the solid is deformed? Suppose if I am applying the external forces, what will be changes? There will be change in the interatomic distance because of due to this external forces. And we are applying some external force which changes the deformation, which tends to change the deform in the size and shape of the body. As a result, generally the atoms and as well as the molecules causing a change in the interatomic distance. So if you consider the interatomic distance between these two molecules will be changes because of this because of this external force. When the deforming forces remove again these intermolecular atomic distances, that means the interatomic forces tends to drive back. These interatomic forces again tends to back to the drive to the original position. This is the story behind it. This property which we are calling as, that means the body when it regains because of due to these intermolecular forces once again, this is calling, we are calling as elasticity. Yes, now you are the student. For example, that means to solve the numericals, to prepare NEET, you should be focused on basics. Until unless without knowing the basics, you will not have proper knowledge solving the numericals. So the next one is, that is called elastic property. That means the property of the material, by virtue of regaining its original position. The property of the material by virtue of its regaining its original position after removing the deformation forces is known as elasticity. Obviously, there are so many examples are there. Quartz, diamond, steel, rubber, these are all the examples. Quartz, diamond, steel, rubber, these are all showing the same elastic property. And of course, during the elastic property, there is no perfectly elastic material exists, but quartz is the nearest perfectly elastic material as far as we consider. So quartz is the perfectly nearest elastic property. No material is perfectly elastic in the nature itself. Somehow, after that's why that is called elasticity. The quite opposite word, obviously you know that plasticity in the property of the material by virtue of which it does not regain its original position. Yes or no, children? Of course, there are so many examples are there. This phenomenon, this property of the material in which by virtue of which it does not regain its original position. Based on the regain to its original position, again the bodies are classified into two types. One is elastic property, elasticity, and another one is plasticity. Example is chewing gum. You know, chewing gum is the best example which I am using here, in which it cannot be regained its original position. Of course, there are solving lead is also example. But no material is also perfectly plastic, but merely putty is kind of that is considered to be as a perfectly plasticity. So the substances which recover partially after the removal of the external forces, we can call it as semi-elastic materials. Semi-elastic material. These are the brief introduction about the elasticity. I will explain and see elasticity concept. Intermolecular forces concept. I hope you understood. Rigid body, deformation forces, restoring forces. Based on this concept, again we are going to divide. That means what do you mean by stress? That is very, very important. Stress. What do you mean by stress? Stress. Of course, you know this stress. So stress is nothing but generally it is the restoring force, not the external force. So restoring force, that means when the deformation forces are removed, immediately within the body, inside the body, within the value of the body, restoring forces develop. If you consider that restoring forces, that means internal forces. Yes or no, children? That restoring forces, if you calculate per unit area, that is called stress. Very simple concept of restoring force acting per unit area. Restoring force acting. That means internal forces are responsible for the restoring force. External force is responsible for the deformation force. So hence if you can observe, if you want to say the definition of stress, restoring force per unit area, the SI unit for stress is Newton per meter square. And of course, you know, Newton per meter square dimension formula is N1 L power minus 1 T power minus 2. Here the stress is again classified into three types. This is very, very important. Already studied. One is the longitudinal stress, and another one is shearing stress. Shearing stress and the value stress. Value stress. See, this is longitudinal, shearing stress, value stress. So very, very important. That means when the force is applied, observe, take this example. Children, if you observe this example, you can easily understand. If a force is applied normal, perpendicular to the body, see, observe this, perpendicular to the body, as I said, definitely these external forces will change the shape. As a result, let the length is L, as a result, the change in length is delta L. So, internal forces will be developed within the body, inside the body. So, whenever external forces, that means the force applied normal to the cross-sectional area of the body, that is responsible for to change its length, then immediately restoring forces also developed within the body, so as per unit cross-sectional area. That is called longitudinal stress, or you can also say this normal stress. Children, normal is nothing but anywhere you should focus on the perpendicular to the unit area of cross-section of that solid. So normal stress or longitudinal stress is defined as it is nothing but the restoring force acting normal or perpendicular to the surface of the body developed for unit area of cross-section. This is also again two types is there. Very, very important. Normal stress or longitudinal stress is then two types. One is a tensile stress, another one is a compressive stress. So tensile stress and compressive stress. This is tensile. This is compressive. See, again these are two types. So one is a tensile stress, another one is a compressive stress. If the suppose if you consider if a rod is supposed stretched with equal forces applied to normal, then restoring forces developed is called tensile stress. The same rod compression under the action of the applied force. So when it is compression under the action of the force, then it is considered to be as a compressive stress. So that is the difference between tensile and compressive stress. Example, you can observe pillars of the building. When the pillars of the building you apply, they are compressed now. They are compressed, so hence the pillars of the building is considered to be as a compressive stress. So there are again two types of stress. One is tensile stress, another one is compressive stress. I hope you understood normal stress or longitudinal stress. Now children, shearing stress. Suppose the same force is applied tangentially. The same force is applied tangentially, which no change in the value, that means length or shape, no change in the value, length or the shape. This is called a tangential force, which is applying that displaces making an angle theta. Suppose if you assume this as a h, this assume as a x, then this stress is called a shearing stress. What do you call this as a shearing stress? That means if the force is tangential to the surface, and because of due to application of the forces parallel to the surface. If you observe, this is one surface, this is another surface. So when tangentially the force is applied, this is also known as, this is applying parallel to the surface. Yes or no, children? And of course, for competitive examinations, we will consider there will be a small change, shearing angle. That means this only the angle which is displaced because of these two, because of due to this tangential force which is parallel to these two surfaces is considered to be very small. So tangential force, that means a force which is tangential, a force which is tangential onto the surface because of due to the application of the forces parallel to the surface, then the stress is known as a shearing stress. This is called a shearing. So shearing stress doesn't change any value, and we can say this shearing stress is because of this tangential force. I am writing this as tangential force per unit area of cross section. That means simply shearing stress definitely changes the shape of the body because of only tangential force. It is responsible. So area of cross section of the body, which is we are calling as shearing stress. Then in liquid and gases, most probably we will consider this volume stress. Example, a gas is enclosed with a piston. A gas is enclosed in a vessel with a tight piston. Definitely when you
there will be decrease in its, if you apply the pressure, obviously. So here, what is happening, there will be change in the value definitely. So when normal stress, that means when a value stress is always considered only in the case of liquids and gases only. So value stress means, suppose the pressure is applied, there will be decrease in the value. That means suppose if you consider like this, pressure is applied equally, then V minus delta V is the decrease. Initial value is V, final value is, then change in the value will be decreases. Then such kind of stress is called value stress. Value stress means it is nothing but the normal force by surface area. Again, we will consider this as pressure. So value stress, that is equals to normal force by area, that is nothing but force by area, that is nothing but pressure. See, that is nothing but pressure. So these three are very, very important. Stress is classified into three types. One is normal stress or longitudinal stress. Again, it is classified into tensile and compressive. Then second one is shearing stress because of tangential force, which displaces or making an angle theta. If h is the total length or height, whatever x is the displacement, you consider this small angle theta also, we get x strain also. So these are the three types of stress. Okay, so now, as I said that whenever the external forces is responsible for the deformation and internal forces is responsible for the restoring force, similarly, when the external force is removed, definitely deformation forces get removed and the restoring force is developed. Thus, the restoring force is developed because of only this external force. So, as a result, there will be change in the length. Then we are calling that as a strain. strain. So strain is nothing but change in length divided by original length. Yes or no, sir? So strain is nothing but the change in the dimensions produced. The change in the dimensions produced. The change in the dimension, that means lengthwise or area produced per unit original length. That means you can consider as delta L by L. We also represent this delta L sometimes with E. So E by L. As how the stress is classified into 3 types, similarly strain also classified into 3 types. That means strain general definition is a change in original length by change in length by original length, and strain is equals to E by L, no dimensions and no units because it is the ratio of same physical quantity. Hence we can say there is no units quantity. Similarly here strain is also classified into 3 types. One is longitudinal strain, another one is shading strain. Okay, children. Then the third one is a value strain. So same concept again. When if the ratio of that means if you consider a body which is suspended, rod or something, rod or spring, whatever you consider, if the external force is applied on it, definitely this rod will be elongated. Initial length you can consider L, then the elongation or something delta L if you consider, then the force is applied here F, this is the responsible external force, then the strain, longitudinal strain, that is equals to delta L divided by L or E by L, which is called longitudinal strain. So longitudinal strain is defined as change in length to the original length. You can also consider this as elongation. Then the shading strain. Shading strain, as I just explained, when the tangential force is applied, definitely it displaces. It displaces, making an angle theta, and the height is h, and the displacement is x. Then we will consider this theta is the shading strain. Theta is the shading strain. So relatively, that is the if you consider this one face, this is another face. See, observe these two surfaces. So the shading strain means it is the relative displacement between two opposite layers. If you consider this one layer, this is another layer. So this is what we can call as this relative displacement, which is if you consider tan theta in this triangle, tan theta that is equals to the change in the displacement of the body is x or x by this height, that means h. For small angles, as I told you that this is applicable only for small angles, then theta we can ignore this tan value. For small angles, theta is equals to x by h, or you also consider delta x by h, or delta x by L also no problem. If you want to consider this h or L as you wish, so you can take delta x by L. This is called shading strain. Yes or no, children? So because of this strain is due to the change in the shape of the body. The strain is because of the change in the shape of the body. Because of due to tangential parallel force which is applied on the body, which is not normal. I will explain these two longitudinal strain, shading strain by taking one more example, no problem, later on classes. Next, value strain. Here also, the value strain means if the system of forces in equilibrium acting normal to the surface, the system of all the forces are in equilibrium, then the value strain is nothing but change in value by original value. Okay, children? So this is the formula for the value strain. This is also known as bulk strain. But this generally indicated with bulk strain also. So bulk strain or value strain, which we observe generally in liquids and gases, which is delta V by V. Only we are taking modulus, but actually when you apply the pressure, there will be decrease in the value. So we will mention the negative. That is the significance of the negative sign. Always it is negative will represent the negative sign because of due to increase in the pressure, the value will be decreases. Okay, children? So this is nothing but 3 strains. One is longitudinal, shading, and value strain. Similarly here, stress also 3 types. Of course, I hope you understood all these 3 concepts. Now let us understand the behavior of a wire with the help of this stress and strain. With the help of this stress and strain. So it's been observed that you want to observe the behavior of the wire, definitely you want to consider this stress and strain. Of course, you know that formula. This is the concept here. Taking the values of stress on the x-axis, y-axis, stress on y-axis and strain on x-axis. If a graph is plotted, then such a curve is called an elastic curve, stress and strain curve. Of course, we already studied in the PUC about this stress and strain. It's been observed that for an elastic limit, suppose P, E, A, B, C, like that, if you divide these points, you want to clearly observe for a given elastic limit, it's been observed that stress is directly proportional to strain. Yes, sir, already studied. One said, so taking the stress value on the x-axis and strain value on the y-axis, within the elastic limit it's been observed that stress is directly proportional to strain. This is known as Hooke's law. It is also known as Hooke's law. That means there is a particular limit for every wire up to withhold. That means the maximum stress in which the body can regain its original position itself is called elastic limit. The maximum stress here it is the elastic limit. The maximum stress applied or within the which the body regains its original size and shape after when you remove the external forces. When you remove the external forces, how much that maximum stress is required, within that only it regains to its original position or withholds the elastic limit. That point itself is called elastic limit. Again and again I am saying giving a statement of Hooke's law within the elastic limit. Until unless if you don't know the elastic limit definition, you won't understand the Hooke's law. So within the elastic limit, that means the maximum force, that means the maximum stress, not force, stress means again restoring force per rate. The maximum stress applied, the maximum stress in which the body can regain its original position after if you remove the deformation forces, that is called elastic limit. Within the elastic limit, stress is directly proportional to strain, and if you draw a graph, it's been observed within the elastic limit. Next of the graph is straight line passing to the origin, then this is stress, this is strain. Of course, the angle here which gives the slope, this is slope. So slope will give the ratio of stress by strain. So here stress is directly proportional to strain. That means that you remove stress is equals to a constant will come. This is called modulus of elasticity due to strain. And E is equals to stress by strain. Is that what you have? So this ratio, stress by strain, giving a new physical quantity which we are calling as modulus of elasticity. So how can you find out in the objective time? Once if you find out this slope, let's start consider. This slope itself gives the slope itself gives the ratio of stress by strain. So stress by strain means E. That means I can say, how can you find out mathematical slope? Tan theta. Yes or no? So slope is always considered calculated with the help of tan theta. So tan theta is nothing but slope. The slope is equals to modulus of elasticity. So in all these Hooke's law and elastic limit definition, even this curve also you are already studied. If you observe this, see here if you observe, this is breaking point, this is elastic point, this is actually when the stress is applied, it increases, strain also increases. Suppose gradually you are increasing mass. Suppose first of all 50 grams mass is loaded for a spring. Generally slowly you are increasing step by step. Second you are adding again 50 grams. So within this point, this is called obeying Hooke's law. This point P, the point P itself is called a proportionality limit. The point that is the limit up to which stress is directly proportional to strain. So if you increase 50 grams, 50 grams, 50 grams, directly proportional. Stress is directly proportional to strain. Then beyond that point P, I'm just briefly explaining, beyond that P, a very few amount of stress is applied. Just within the less stress, it reaches to the elastic limit. Yes or no? Reaches to the elastic. See, observe this graph carefully. When you increase the mass, within the small stress, it increases and stress is, that means you can say that stress will be increases, that means strain will be decreases, as a result modulus of elasticity will be increases. That is very, very important. See, observe children, here if you beyond that point P, that means if you consider this as A, the point E, this is A, B, C, I am considering according to my, this is called elastic limit. So here after beyond the point P, if we apply a very less, small amount of stress, definitely stress will be increases, but strain will be decreases. As a result, modulus of velocity will be, see, observe carefully. That is the relation between, that means braking stress is also very, very important here. Then, if you remove here at this point, it will reaches to the initial point, original point, where it obeying Hooke's law. But up to reaching the elastic limit, after that, beyond that, it won't obey. If you won't apply the stress, mass also doesn't depend upon the load, even it is constant. See, observe. Here the slope is constant, so modulus of velocity is obviously constant. Observe this EPA. So in this slope is constant, so slope obviously. With the help of slope, we can easily find out. With the help of slope, the students who are having good commanding in finding the slope of this type of curves. Observe the slope here, E to A and A to B. Similarly, B to F, similarly B to C. The point B itself called a breaking point, where the maximum stress that the material can withstand without breaking is called breaking stress. Okay, so I am not going to deeply all this. So stress is directly proportional to strain, and E is equals to stress by strain. This modulus of elasticity is again classified into 3 types. Obviously, you know Young's modulus of elasticity and bulk rigidity. Sharing. The 3 parts are 3 types of stress are Young's modulus of elasticity, bulk modulus of elasticity, and rigid modulus of elasticity, which I am going to explain one by one, and all the formulas I am going to derive. See, children? So, modulus of elasticity is classified into 3 types. So, E. Obviously, you know, we are already studied in PUC. The first one is Young's modulus, which is represented with Y. And second one is rigidity modulus, and the third one is bulk modulus. So let us first study Young's modulus. First one is Young's, which is represented by Y. So Young's modulus of elasticity, that means it is nothing but, first of all, Y is equals to longitudinal stress by longitudinal strain. This is the formula for Young's modulus. I am going to discuss all the cases now this. So Y is equals to F by A, restoring force per unit area, by delta L by L. Okay, children? Then F by A, if you consider this as E by L, then it is considered to be FL by AE. So finally, the formula is Y is equals to FL by AE. Suppose when a rod is suspended and this external force is applied, then because of the mass is M, then F is equals to, we can consider as mg, then mgl by, what is the formula we are going to get? Y is equals to FL by AE, that is equals to mgl divided by area of cross section, assuming that it is in the form of uniform area of cross section. That means we will consider as pi r square. So only solids can have this kind of stresses. So Young's modulus. Liquids and gases does not possess a Young's modulus. So mgl by, we will write pi r square E. So this is the formula to find out the Young's modulus of elasticity. Okay, children? So Young's modulus of elasticity y is equals to mg. Sometimes they ask for even see y is equals to f by fl by e into fl by a. So e is means changing length. So e is equals to f e is equals to fl by ay will come. That means e is equals to f by ay into l. See, this is e, this is l, this is f by ay. Sometimes they ask for the e also. Okay, children? If you want, you can write down formula, all formula y is equals to fl by ae, that is equals to mgl by. Sorry, Sinan, sorry for the interruption. It will be a power loss. Okay, I think the voice is audible for you. So here, the formula for Young's modulus to find out is FL by AE, to find out the changing length F by AY into E. The next concept is the same in Young's modulus. One more concept is there. In the case of spring and rod, suppose if a spring is suspended and the load is attached to it, obviously you know that F is equals to the restoring force is equals to Ky. I am taking magnitude only. Kx or the elongation is x, where K is called spring constant. You know very well. K is called the spring constant. Yes or no? Similarly, when you consider a rod, in case of rod, same mass is attached, then you will get the same concept here also. But the formula is y is equals to F by A. Apply this. Y is equals to F by A by E by L, as I said you before. Just the same formula. Therefore, you will get the K is equals to same concept here. How F is equals to Kx? Similarly, you are going to get F is equals to Ya by L into X. You are going to get. So F is equals to Ya by L into X. So it is similar to that of. So F is equals to K into X. So how here the spring constant will come the same manner. In the case of rod, when a mass is attached, this Ya by L is known to be as constant, or we consider as K. See, analogous similarity between a spring attached to a mass or a rod attached to a mass. So Y is equals to, the formula is F by A by E by L, or Ya by L into X, or F is equals to Kx. That means the constant we are taking is Ya by L in the case of rod. Okay, children. Next, see some other. If you develop this formula, because so many problems are there in objective based on the Young's modulus. Before going to this two, Young's modulus of Young's modulus, I'll once again see y is equals to FL by A, that is equals to. So if you take that FL by A, and again if you multiply with A and here A, multiply and divide with. So F is L into A, area into length, we will consider as value. This is value by A square into E. So that whenever value is constant, you can apply this formula. That means FB by A square into E. So you can also find out the value, okay, which is y is equals to, in terms of y is equals to, you can also consider as y is equals to F into, F means the force, B is the value, and A if you consider as pi r square, then you will get pi r power 4 into E. Yes or no, children? So here r power 4 is going to get. Y is depending inversely proportional to its r power 4, and the value is a constant. Then you will get y1 by y2 is equals to r2 4 by r1 4. It depends how, in the radius. So density is equals to, what is the formula? Mass by value. Yes or no? Density is equals to mass by value. When you take that value is equals to mass by density, substitute here. Therefore, F is equals to, y is equals to F into, in place of value, mass by density into pi r power 4 e. These are all development extension. So that means if you consider this Fm by d into a square r pi r power 4 into e. So in the above formula, f, v, y are the same. If you take this f, v, y, if you consider this as v, no problem, f, y, v. Observe carefully. They are all same. That means for the two y's, then if suppose y, f, v are same, how related to e? E is related to, is inversely proportional to a square. That implies e is inversely proportional to 1 by r cube. These two formulas are very, very important. We are using these two formulae to solve the objective type. Once again, I will explain. Y is equals to fl by a divided and multiply with a, and you are going to get a into l. Area into length is equals to value. That is nothing but a into a square into e. If you want to consider area of cross section is uniform, then pi r square will come. Here, sorry, pi square will come, because a square means pi r square whole square. That means pi square into r power 4 you are going to get. Understand now? So this pi square is constant, no problem. Absolutely 3.14 whole square. So when again density is equals to mass by value, so substitute value is equals to mass by density in place of value, you will get this formula. Or if you consider this as a square also, no problem. Sorry, here also square will come. Okay, no problem. Pi square into r power 4 area. So like that, E is elongation is inversely proportional to its a square, and also it's inversely proportional to r power 4. That is very, very important. That means when a body of mass having the same force, same value, same Young's modulus, then the relation between elongation and area of cross section, the relation between elongation and radius is these are the two important formulae. One more is there. When a body of still value Young's modulus. So Young's modulus case is very, very important. Before going to these two concepts, I would like to explain all the formulae regarding Young's modulus. So Young's modulus general formula is longitudinal stress by longitudinal strain, F by L by delta L by L or FL by AE. If you develop that, you are going to get it's all applicable in other forms of the Young's modulus. So here, see one more. F. So we will take all y is equals to F by L by E by L, F by A, sorry, F by A. Therefore, that is equals to FL by AE. FL by AE. Where y is the Young's modulus. Now, I am going to multiply with L on both divided. This is L. So, why are all new? Because in the denominator, I am going to get value also. So, in the denominator, A into L, you can take V. So, y is equals to F into L square divided by A. L means nothing but taken as value into E. This is also one kind of form of Young's modulus in which you consider Fl square by EV. Again, if you apply the value is equals to density is equals to mass by value, density is equals to mass by value, or value is equals to mass by density. Therefore, y is equals to Fl square by value mass, this is density, and E. Isn't that? So Fl square d by Me. So M is the mass of the wire, d is the density of the wire, and E is the elongation, V is the value, and A remaining you can apply in the case of whenever y, f, d, e, l, m all quantities are given in the problem, you use this combination. When suppose R area and value about f, y, f, v area, then you can use this combination. So in case of length, this formula is applicable. In case of area, this formula is applicable. Okay, so then, and next, in a body of still, if you want, you can you can write all these formulae in a A4 sheet and try to submit to WhatsApp. Children, until unless without having good commanding in all these formula, I won't be able to solve the numericals. Okay, next, write down. That is very, very important. When a body of mass M density is suspended from a wire and in a elongation, suddenly the same, see, if a body is suspended with the help of a mass in A, the density D, okay, and it is suspended. The mass is m. It is suspended in air, and the elongation is e. And the elongation is e. So when the same operators, the same system is immersed in a liquid, that means if the body is completely immersed in a non-viscous liquid of density dl, the density of this is A now, so the A, if the same is immersed in a liquid, then the relation between elongation E dash is equals to E into 1 minus dl by dv. E into 1 minus dl by dv. So this is the formula when if you want to apply in the case of elongations. That means if suppose a body is suspended, having mass m and density d, especially it is in A now, and having elongation e, then the same operators, that means the same system is now immersed, completely immersed in a non-viscous liquid than any liquid, then we can use this formula to solve E dash is equals to E into 1 minus dl by dv, where dl is the density of the liquid and dv is the density of the body which is suspended here. So this is the density of the body suspended here. Here density of the liquid. E dash is the elongation after immersing completely in a liquid. So these are all the concepts related to, if you want you can solve previous years, need previous years concepts based on X models. So many problems are there. You try yourself, and of course next models. So models of velocity is classified in 3 types now. What are the 3 types of that? The first one is Young's modulus of elasticity. That is very, very important. Young's modulus of elasticity. And some problems are there. If you open the module, page number, I will solve the problems, 1 or 2 problems, example problems in the material. Children, the material provided by Nandi is extraordinary, dealing with the previous NEET problems and all the exercise problems, example problems given for you to help to solve the objective type 3rd level. So I suggest you please focus on our material only, don't go with the other material as of now. Once if you finish all the exercises, level 1, level 2, homework, classwork problems, then you can go with the other module. So I suggest you page number, example problems, we'll try to solve the page number based on Young's modulus, page number 91. Page number 91, mechanical properties of solids module. So you just if any page number is changed, I will send to WhatsApp, no problem. So you will solve the examples, all the examples, illustrations which is given in the material. Okay, sir. The next 2 are modulus of rigidity or rigid modulus. Okay, sir. We will get the next class.
Need the postmortem. బ్రేక్ ఇమ్మంటారా?
ఆన్ చేయండి.
హలో,
హలో
తీసాను సార్. నేను సార్ దీంట్లో
హలో
హిందీ వచ్చింది సార్. బట్ ఇంట్లో ఇది ఆడందా? రీస్ట్ అవ్వాలి దీంట్లో. కొద్దిగా పాస్వర్డ్ చాలా తక్కువ ఉంది సార్. మొబైల్ నెంబర్
చెప్పండి.
90 సార్. సార్ నేను ఫోన్ తేలేదు సార్.
మైక్ పట్టుకున్నట్లు
సార్ చూడండి, మళ్ళీ నాయిస్ బాగా వస్తుందంటే మాస్క్ పెట్టుకుంటే రావట్లేదు. మాస్క్ పెట్టుకుని చెప్తాను.
మాట్లాడండి.
హలో స్టూడెంట్స్. హలో స్టూడెంట్స్.
హలో
హలో స్టూడెంట్స్.
వచ్చింది.
వచ్చింది సార్. ఇప్పుడు కనెక్ట్ అయింది సార్. కనెక్ట్ అవ్వాలి. హలో స్టూడెంట్స్.
హలో స్టూడెంట్స్. ఓకే సార్. ఇప్పుడు హలో స్టూడెంట్స్. హలో హలో నాయిస్ వస్తుంది సార్. మైక్ పెట్టుకుంటాను. మైక్ పెట్టుకుంటాను.
మెసేజ్ పెట్టాను.